is temperature and thermal properties of materials. We have discussed the temperature and other things related to the resistor, correct? So now, if we want to sense the temperature or thermal properties of material, how we can sense it, how we can design different sensors, means what sensing principles we can apply here. So for that, what we can see, we can observe the human bodies, means they have a sense of temperatures. We can sense, you can also sense, just by observing the things. Okay, if at a particular region, if you see fire is there, then definitely you will see that region is hotter than where we are. But we can sense, but we cannot measure this accurately. Okay, we can easily tell the difference between the warmer and cooler objects. Then what is going on with these objects that they produce different perceptions? Okay, uh, uh, so because exact measurement is not possible by us, so that's why we have to have some mechanism by which we can exactly determine how much hot the hot region is, the particular region is as compared to the cooler one. Okay, so for that, look into the matter, means different types of materials. What happens there? Every single particle in this universe exists in perpetual motion. If we consider anything in this world, and of that anything, a single particle that will have some perpetual motion. The temperature of a volume of material in the simplest way can be described as measure of an average kinetic energy of vibrating particles. Stronger the movement, the higher the temperature. So if we have an object, okay, a nucleus will be there, surrounding nucleus, number of electrons will be moving, etc., etc. So every single particle, this will have some motion, okay, and then corresponding to the volume of material, what we will say, uh, motion involves there, so definitely some kinetic energy, and from kinetic energy we can say it is having some temperature. The stronger the movement, higher the kinetic energy, higher the temperature. Correct? Is it clear or not? So if we look into the atomic structure, molecules and atoms in a given volume of material do not move with equal intensities that we know. Thus, they all are at different temperatures because their movement, intensity of movement is not equal. They will not have same kinetic energy. So definitely they will be at different temperatures. The average kinetic energy of large number of moving particles uh, determine microscopic temperature of an object. So what we can determine the macroscopic, sorry, not the macroscopic temperature of object we can determine by observing the average kinetic energy. So in this particular case here, however, we are concerned with methods and devices that are capable of measuring the macroscopic average kinetic energy of vibrating particles. Or alternatively, what we can say, the devices that can measure the temperature of the object. So by measuring the average kinetic energy. Okay, since temperature is related to the movement of molecules, it is closely associated with pressure, which is defined as the force applied by moving molecules per unit area. When atoms and molecules in material move, they interact with other molecules and transfer a portion of its kinetic energy, so the never start vibrating more intensely. I think these things are known to us. What happens when they are moving with different kinetic energy? They interact with nearby atoms, and in this way they transfer their own energy. I am saying here the portion of its kinetic, maybe complete kinetic energy will be transferred to the nearby atom, okay, nearby particle. So the nearby particles or atoms, they start vibrating more intensely. Why? Because they are vibrating itself they have its own kinetic energy, and if they are getting kinetic energy from never atoms, then their vibrations will be more. They will have more kinetic energy. Now this agitation propagates through the material, elevating the temperature. So what happens? This increases the kinetic energy, ultimately increases the temperature. And an atom contains moving electrons swirling around its nucleus like a cloud of electrical current. So thermal agitation causes that current to produce electromagnetic wave. Now ultimately what happens? This is the physics involved behind it. When this agitation propagates through the material, elevating the temperature, it's clear, means this is propagating, kinetic energy will be more, so temperature will be more. Now what happens in case of atom? It contains number of electrons moving around it, as we know in s orbit, p orbit, d orbit, etc. Like a cloud of electric current. And thermal agitation causes that current to produce electromagnetic wave. So ultimately what happens? A kind of electromagnetic waves are emitted by that atom. What is the cause of that? The kinetic energy means agitation means temperature. So hence every vibrating atom acts as microscopic radio transmitter, which emanates electromagnetic radiation to the surrounding space. So this is the ultimate effect of what? The thermal property of material. Okay, because of this, because of the movement of electron, uh, what happens? If they strike with each other, then they transfer a portion of their kinetic energy to neighbors, and then the neighboring atoms or particles, they will vibrate more intensely. And if intensity will be more, vibrating intensity, this will be more, then definitely the temperature will be more. Okay, so if we look into the atom, the structure of atom, surrounding nucleus, number of electrons are moving. Okay, uh, this vibrating atom acts as a microscopic radio transmitter because of the electric current, the cloud of electric current and thermal agitation. This causes the current to produce electromagnetic wave. So that's why these atoms may act like a microscopic radio transmitter, which emanates electromagnetic radiation to the surrounding space. So in this way, electromagnetic radiations comes out from the atom, and because of the thermal property of material. Okay, so if the metal is having some thermal properties, so then it may uh, radiate the electromagnetic waves of certain frequencies. And if we are able to capture these waves by any mechanism, then we can measure this. Now, these two types of activities, means the radiation, form a basis for heat transfer from warmer to cooler objects. So, because of this warmer object, the radiation of heat will take place, and then the heat will be transferred from a warmer to cooler object. The two bases are, one is the conduction, other is the radiation. Okay, so the stronger the atomic movement, the hotter the temperature, and the stronger the electromagnetic radiation. If we know the movement, atomic movement is large, definitely more temperature will be associated with that atom, and the strong electromagnetic radiation may come out from it. Okay, so a special device, we will call it a thermometer, which either contacts the object or receives its electromagnetic radiation, then produces a physical response or signal, and that signal becomes a measure of the object's temperature. So ultimately goal is to measure the temperature of that material. And how we can measure? By this principle. So this is one example, the thermometer. That is a sensor. We can sense the temperature of a human body. Simple. So while touching the object, or there may be several types of thermometers that receives the electromagnetic radiations and ultimately convert these radiations into the temperature, so that we could say the temperature of this particular material or particular object is this one. So this is another principle. Now, to measure the temperature, we may have different scales, and I hope you are familiar with these scales. Uh, the different definitions are associated with this scale. One is the Kelvin, one is Celsius, one is Fahrenheit. Okay, so 0 Kelvin, different definitions are developed by scientists, researchers. Newton's developed some definition. Some other Kelvin also developed a definition. One definition I remember, actually, I don't know exactly, a point at which all the states of matter present, means liquid, gas, solid. That is called Kelvin temperature, 0 or reference Kelvin temperature. So these three scales, they have relation. So if we have a temperature in degree C, okay, then we can correlate it with the Kelvin. So temperature in degree C can be written as temperature in Kelvin minus 273.15 degree. So standard formulas are available. You can see it. Similarly, Fahrenheit temperature can be related with the degree C by Fahrenheit equals to 32 plus 1.8 degrees C. So in this way, we have different scale, and if we want to convert temperature in one to another, we can do it with different converters, etc. So if we have a sensor that is capable to sense the temperature of an object, and suppose it is giving temperature in Fahrenheit, but if you want to see in Kelvin, so you can calculate using pen and pencil, or you may have some alternate way associated with the same measuring device that will also give the display the temperature in degree C. So Kelvin, degree C, Fahrenheit, whatever is the case, we can get it. Okay. Now, the thermal expansion, another measuring principle. So thermal expansion simply means that, suppose if we are present, if we are residing in a place, means you are sitting at the different places. What happens if all of a sudden temperature of your place rises? The temperature will increase. Definitely, the agitation of molecules and atoms will increase. Okay, and when the temperature goes up, an average distance between atoms increases, which leads to an expansion of a whole body. The change in dimensions for maybe length, maybe width or height is called linear expansion. So thermal expansion is useful phenomena that can be employed in many sensors where thermal energy is either measured or used as an excitation signal. So suppose near uh, in case of power generating sources, there are boilers. Okay, so near a boiler means where the water gets boiled. So to control the temperature or to sense the temperature so that it should not cross the threshold level, we need some measurement. Okay, so this can be done using the thermal expansion principle. So we can design a sensor by which we can measure the temperature. Okay, so that is another way by sensing the temperature. Then heat transfer. There are two fundamental properties of heat. We all know, we all are familiar with these two fundamental properties. Number one, the heat is totally not specific. That is, once it is produced, it is impossible to say what origin it has. Okay, the heat is heat. We cannot say something about its origin. Okay. The second one, it cannot be contained, which means that it flows spontaneously from warmer to cooler part of the system, and there is no method known to modern science to stop the heat flow entirely. We cannot stop. We cannot keep this generated heat at particular point. Okay. Uh, by nature, it flows from higher temperature region to lower one. Okay. So thermal energy may be transferred from an object to another by three ways. And these three ways are conduction, convection, and radiation. Either the heat will be transferred from one body to other because of conduction mechanism, because of convection, or because of radiation. Conduction and radiation relates to solids, liquid, and gases, whereas convection can transfer heat via an intermediate fluid, liquid, or gas. So we will see here with the help of one figure diagram, a measurement of any physical quantity always requires transfer of energy. Naturally, one of the objects involved in thermal exchange may be a thermal sensor. So suppose we have a heat source, as I told you about the power generation plant, where we have some boiler. Okay, so the boiler, let's consider a thermal source. Now we want to, although a good strong mechanism is used to control the temperature there, but for a layman language, what we can assume, suppose the in front of, the boiler where boiler exists in surrounding of that, a temperature may not increase. So what we can say, so boiler, suppose it is acting like a heat source. So if it is in contact with some other material, then heat may propagate to that material because boiler is hotter. The other material which is in contact with the boiler may not be hotter. So heat may propagate from boiler to that through conduction. Suppose there is no other material that is in contact with the boiler. So what may happen? The heat may radiate it to the surrounding, or through air convection, the heat may flow to the surrounding. So in this way, the heat flow can take place, and we can design a thermal sensor to measure that heat transfer, to measure that heat flow. So its purpose would be to measure the amount of heat which presents a certain information about object producing that heat. Such information may be temperature of an object, maybe chemical reaction associated with the object, maybe position of the object, etc. etc. For example, if we fire a bullet from bullet gun, okay, and if that bullet strikes at a point, what will be the effect of that? When it strikes an object, it may produce a very high temperature at that particular object. So if we are having a device, a sensor that could measure this temperature, so what we can do? We can design a shield for anyone, for human being, for soldier, etc. So that bullet will strike the shield, but it may not damage the object, because whatever temperature is generated, whatever force uh, it dispenses to the object, that can be absorbed by that particular shield, and it will not damage the object. So that is the purpose. So that's why we can design a thermal sensor. Now, these three principles you have studied in your physics at 12th level, or maybe at first year level. Uh, with this, we can design the sensor. Now,